Let W be the set of matrices A, B, B, C, where A, B, and C are real numbers. Consider the following questions. The first is, show that W gives a subspace of the vector space of 2 by 2 matrices with real entries. And the second question is, give a basis for W. So in order to answer part A, we have to show two things. We want to show that if you take any two matrices from W, their sum is also in W. And if you take a scalar alpha and a matrix from W, say A, then alpha times A is also in W. So let A and B be matrices from W, and let alpha be a real number. Say A is given by the following, and B is given by this, where A, B, C, A prime, B prime, C prime are real numbers. Then A plus B is simply A plus A prime in the top left entry, B plus B prime in the top right entry, B plus B prime in the bottom left entry, and C plus C prime in the bottom right entry. Now, all these entries are real numbers. As well, this entry and this entry here are equal. So this is in W because we have a matrix of this form here. Now let's look at alpha times A. Alpha times A is simply the following. Again, all the entries in this matrix are real, and this is equal to this. So we can say that this is in W. So W is closed under addition and scalar multiplication. So W is a subspace of the 2 by 2 matrices with real entries. So it's a vector space. We can find a basis for W. Now, one basis for the set of 2 by 2 matrices is given by the following. So if we take these four matrices, they'll give a basis for this. And we see that the matrices in W are more restricted than the set of all 2 by 2 matrices. In particular, the matrix 1, 0, 2, 3 is not in W. So W is in fact a proper subspace, and so it will not have 4 elements in the basis. Now, let's first see if we can write down matrices whose span is W. For that, notice that A, B, B, C can be written as A0, 0, 0 plus 0B, B0 plus 0, 0, 0, C. And this can be written as A times 1, 0, 0, 0 plus B times 0, 1, 1, 0 plus C times 0, 0, 0, 1. And so the span of these three matrices will give you W. So the next question is, are they linearly independent? Remember how we can check linear independence. We set this to the zero vector, in this case is the zero matrix, and ask if there are solutions for A, B, and C such that not all of them are zero. But if you look at this matrix here, the only way for this to be equal to the zero matrix is for A, B, and C to be zero. And so the only linear combination of these three vectors that will give the zero vector is to take all the scalars to be zero. And so these three matrices are linearly independent. So they are linearly independent and they span W. So that will give us a basis for W. And so the dimension of W is 3, since there are 3 elements in a basis for W.